All right, so we can get started. Thanks everyone for coming. Today we have Professor Bhupal Dev, who's a physics professor here since 2016, and he'll tell us about new probes of new physics in the multi-messenger era.
Good afternoon, everyone. So today I'll be talking to you about new probes of new physics beyond the standard model in the multi-messenger era. So before I start talking about new physics, maybe I should talk about old physics. And maybe we can start with very old physics. That's the atom. So in the very early days, it was thought that that's the basic constituent of matter. But now we know better. And if you zoom into the atom, we find that it has some structure, as Mr. Rutherford had told us. And so you have the protons and neutrons inside the nucleus, and that's about 10,000 times smaller than the atom. Then you can zoom in further, and if you look at the individual protons and neutrons, you find that they're also not fundamental objects. They are made up of what are called the quark, and they're about 100 million times smaller than the size of the atom. And then also we have the electrons going around the nucleus, and the electron is also fundamental, and the size is at most 10⁻80 meters, and that's the size that we have probed so far. Because the size is inversely proportional to the energy, and the energy we have gone so far is the highest energy we have achieved with Large Hadron Collider, which is our TeV scale, and if you convert that, you get like 10⁻18 meters. So that's the length scale we are probing at the moment. So we don't know if these objects have structure below this energy scale, but that's what we have so far. And it turns out that these quarks and electrons, they come in different flavors or different generations, and then we can arrange them nicely like we do the elements in the periodic table. And this is our periodic table called the standard model, where we arrange the particles in this way. So the upper part, these are called the quarks, as I told you before, but now we have 6 different types of quarks, upcharge top and downstream bottom. And below we have what are called the leptons. There are 2 types of leptons. One are the charged leptons, like the electron, and it has 2 heavier cousins like muon and tau. And then we also have the neutral leptons called the neutrinos, again 3 different flavors. Now in the inner circle, what we have are the force carriers. Now in the standard model, these particles, they're the matter fermions, they are spin half objects, and the way they interact between themselves is by extending the force carriers, which are gauge bosons, which are spin-1 bosons, right? So we have these 4 different types of gauge bosons because we have 3 different interactions to explain in the standard model. The electromagnetic interaction, whose carrier is the photon, and then we have the strong interaction, whose carrier is the gluon. They're both massless. And then we have the W and the Z bosons. They mediate the weak interactions, which are responsible for nuclear bed decay. And these are heavy. Now all these particles, they are massless in the early universe when they're created, and somebody has to give them mass. And it turns out that this guy here, Higgs boson, that's what is giving mass to all these other particles after what is called the electroweak symmetry breaking. Okay. So it seems like the standard model is complete after the discovery of the Higgs boson, and it beautifully explains many different phenomena in nature, and it works extremely well. Okay. In fact, it's also very simple. You can write it on a coffee mug, so when you come to seminar by particle theorists, you must see a Lagrangian. So that's why I'm showing the Lagrangian. And this Lagrangian has 4 different terms, and these terms are actually very simple. The first term just tells you how the forces are acting, and this is nothing but just like a Maxwell equation. So if you just take this term and take the Euler-Lagrange equation, then you get the Maxwell equation for the electromagnetic force, right? And similarly, you can get it for the other forces. Then the second term here, there's nothing but the interaction term of the matter with these forces. So it's just tells you how the forces are acting on the matter. And then the third term here, that tells you how these particles are getting mass. These are called the Kawa interactions with the Higgs. And when the Higgs gets its vacuum expectation value, then all these particles get mass. And then the last term here is just tells you how the Higgs particle is working. Okay, so that's the scalar potential in the standard model, and that governs the behavior of the Higgs. So as you can see here, so it's very simple, in technical language. So this is a direct product of these three different gauge groups: SU3 color for the strong interactions, then SU2L for the weak interactions, and U1Y for the hypercharge. Okay, so if it works so well, then why do you need to consider going beyond it? Well, before we do that, so let's just pause for a moment and just see how really beautifully standard model has been working. So this is a picture, it's a recent picture from earlier this year, taken from this Atlas collaboration at the Large Hadron Collider. You don't have to know all the details here, so you can just pay attention to this y-axis here, which is the cross section of different interactions in some units, picobunds. It basically means 10⁻⁻36 centimeters squared. And on the x-axis here, you have all these different processes. Now, these processes they can be strong interactions, they involve weak interactions, electromagnetic interactions, and so on. So everything has been has gone into this. And all you have to look at is the prediction from the standard model theory, which is shown in this gray, and then this the different data points, which are shown by different colors, depending on at what center of mass energy the LHC was running. And you can see that for almost all these observables, we have exquisite agreement between the theory and the experiment. And that just tells you how well the standard model is working. Okay, and sometimes we hear these comments that LHC has not been successful because it did not find any new physics. But actually, that's that's not a very fair comment, because the LHC has been successful, and this is the success of the LHC. Okay, that we have been able to measure the standard model so precisely using the LHC. And there is also many more years to go for the LHC to run, and we'll get many more precise measurements like this one. So if the standard model has been so successful, as I said, then why do you need to go beyond? Well, it turns out that it is incomplete. Okay, and why is it incomplete? Well, there are evidence, and there is ample evidence from both empirical observations as well as from theory considerations. So first, let me just tell you about the empirical observations. One is this observation of neutrino oscillations. We have three different flavors of neutrinos, and it turns out that all these three flavors, they oscillate among themselves. And there have been many experiments from solar, atmospheric reactor, accelerator, and so on, which show that all three neutrinos oscillate within themselves. And that just means that at least two of the mass eigenvalues have to be non-zero. Okay? And in the standard model, there is no way you could give mass to the neutrinos, and that's why we have to go beyond the standard model. The second piece of evidence comes from astrophysics, so all the particles that we saw in the earlier slide, the standard model describes, that can only explain about 5% of the observable universe, and that's a bit embarrassing, but that's what it is. We're working hard. So far, no luck. About 90% of the universe seems to be dark, and we don't have any better term for that, so we just call it dark matter and dark energy. Okay, and there is no candidate in the standard model to explain this. The other piece of evidence that comes from the fact that we all exist, because the universe seems to be matter-antimatter asymmetric. There seems to be a lot of matter, but no ambient antimatter in the universe. Because if you look at the fundamental equations, they are symmetric for both matter and antimatter. So why should there be asymmetry? And it turns out whatever CP violation the standard model has, that's not enough to generate the level of asymmetry that we need to explain the observed data. So that's one of the strong evidences for going beyond the standard model. Now, these are the empirical evidences, but there are also some theory considerations, or what I call the aesthetic points, which also point something towards beyond the standard model. I mean, of course, it doesn't have to be satisfied in a beyond standard model theory, but if it is, then that's that's just it just makes it more beautiful. One of the examples is this gauge coupling unification. We all know from quantum field theory that the coupling constants are not exactly constants. They run with different energy, and if you go to higher and higher energy, then these couplings have different values. And if you just plot it as a function of energy, you find that they don't meet at one point. But there are models going beyond the standard model where they actually meet at one point. So that kind of suggests that maybe there is something deeper that the couplings should unify at some higher energy scale, where standard model does not do that. The other kind of theoretical issue has to do with the Higgs boson itself. Now, I just mentioned before that the Higgs boson gives mass to every other particle, but its mass itself is unstable in the standard model because it's a scalar particle, so it's not protected by the chiral symmetry. And in fact, there is a quadratic divergence to the Higgs mass. So the Higgs mass, so it will tend to live at the scale of the, so whatever energy scale goes in the loop. And the only energy scale that we know of is the Planck scale. So if you put the Planck scale here, you get a huge number. But what we have observed is just 125 GeV Higgs from the LHC data. So in order to get that, you have to make some cancellation. And cancellation like 1 part in 10⁻⁴ or something. The huge cancellation you have to make in order to make between the bare mass term and this quadratic term in order to make the Higgs mass whatever we have today. So this is known as the gauge hierarchy problem. And so this is a big issue. I mean, you could just live with the fine tuning. We know there are other things in nature which are also fine tuned. But if there is a theory which cures this fine tuning, like in supersymmetry, then that would be really nice. The other issue is also what is called the flavor puzzle in the standard model. If you look at the mixings between the different quarks, they're almost diagonal. Okay, so you have the diagonal entry is pretty large and off-diagonal entry is kind of small. This is the Capillo angle, and then this is the 1,3, which is very small. But if you look at the lepton sector for the neutrinos, then it looks kind of anarchic. Okay, so it doesn't look diagonal by any means, and so there is some hope that maybe there is some theory at higher scale where there is a single mixing, and then from there you can derive this just by the renormalization group running. But at the moment we don't have a compelling theory to explain actually this in a nicer way. So if we have all these different problems in the standard model, then we must have to go to some beyond standard model physics, and that's what we are doing. So the search for new physics, you can understand in a very simple way here from this diagram. So we have this energy scale on the x-axis and some interaction strength on the y-axis. Now on the top left here, that's the low-lying fruit. So if the energy scale is small and the interaction strength is large, that's something that we have already found, right? So that's the known physics. And then if you go to the right in this on this axis, then you're going to higher and higher energy scales. And that's the energy frontier, right? So you pump in more and more energy and see if some new particles come out. That's what the Large Hadron Collider is doing. And the future colliders will also do the same thing. And there you can try to find heavier and heavier particles, which are the new particles or the messengers for the new physics. But you can also probe in new physics in a different way. Instead of going to just large energy, you go down in interaction strength. Okay? You go to this is called intensity frontier. You shoot very intense beams of silicium muons, and then you shoot it on a target, and then see if you can produce some hidden sector particles. These are usually called the beam down type experiments. And so these experiments kind of they lie in this part of the parameter space. They probe very small interaction strengths. But there is also a wide swath of parameter space here which cannot be probed by any of these beams, right? So if your new physics, if you're unlucky and your new physics lies somewhere over here, then there is no way you can probe it either by this or by that. So what we need is actually joint effort or a synergistic effort between these different frontiers to see if we can really somehow cover this entire part of the parameter space. And in terms of the DOE lingo, these are the three different frontiers. You have the energy and intensity frontier, but you also have what is called the cosmic frontier. And many of us will work on this. We do really like it very much. So what does the cosmic frontier do? So it also has some overlap with these other two frontiers, but by itself, it also can maybe tell us something about this part of the parameter space, which neither the energy nor the intensity frontier can access. Okay. So this can be explained by a very nice cartoon, which I took from this talk by Raman Sundram, who inspires me a lot because he was my teacher, Maryland. Let's say you're hiking in Colorado, snowmass, and you see all these different peaks. These are these peaks for new physics, and you lose your way. Then what do? You can go back, or you can seek some help, and the help could come from the sky. So this is what the cosmic frontier does. It gives us some, when we are lost, doing either this one or this one, then we can get some help from the sky. Okay, so that's the motivation. Okay, so in the last 10 years, we did get some big help from the sky. And it turned out that there are two major breakthrough discoveries in the last 10 years, which have revolutionized our understanding of the universe. The first one is the detection of high energy neutrinos by the IceCube Neutrino Observatory. Okay, here are some nice pictures showing this, showing some event displays, and these are real events taken at IceCube, which are basically photomultiplier tubes. When neutrinos pass through ice, it produces charged particles which emit certain flow of light, and is just picked up by this digital optical modules, and it just lights up models. This is what you see here in this picture. Apart from this, more importantly, what IceCube has found is that they could identify some of these sources of these high energy neutrinos. Okay. So in fact, in the first, I think in the first publication in 2017 or 2018, they found like 18 events which are correlated to a particular blazar. Now, blazar is nothing but just active galactic nucleus, where you have the jet pointing directly towards you, so you get large intensity of gamma rays, and so they could really pinpoint using timing and the directional sensitivity of IceCube, and looking at the Fermi gamma ray monitor, they could really point out that some of these events were coming from this particular blazar. And now they have even more events correlated with blazars. In fact, they have 88 of the total 160 some events which are correlated with 4 different blazars. So this is really a multi-messenger physics, where you're looking at different particles coming from the same object, neutrinos and gamma rays. On the other hand, in parallel, there was another very important development that happened, which was the detection of the gravitational waves by the LIGO Observatory. You all have heard about this. So we had this binary black hole merger, and after this, LIGO discovered something even more spectacular, which was discovery of the binary neutron star merger. Okay? And I'll discuss later why this is important for new physics searches. So in this case, they have the multi-messenger signal. They had the gravitational waves as well as the gamma ray burst that came from this catastrophe. Okay? So this is really a new era in multi-messenger astrophysics, and apart from giving us opportunity to study astrophysics, it also gives us new opportunities to do new physics searches, the fundamental physics searches. That's the main point I would like to drive home in this talk. Okay. So what I'll do from now on is I'll discuss I'll take a few examples from my own work and tell you how these two discoveries have helped us in understanding at least or constraining new physics beyond the standard model. Okay. So I'll start with the high energy neutrinos, and so there are many possibilities that you can consider. Due to lack of time, I'll only consider a few of them. So these are mostly work done with my graduate students. So this decaying dark matter, supersymmetry, and non-standard interaction, they all have been done in collaboration with my first graduate student, Ichon Sui. And then there are also some other works that are done with Gaurav Chauhan, and also some collider complementarity with Fangzhou. But as I said, due to lack of time, I'll only consider the dark matter and the NSI and relic possibilities. I'll leave out the supersymmetry part. If you have any questions afterwards, please feel free to ask. So before going into the details of these new physics probes, let me first just give a brief overview of the IceCube. Some of you may not have seen it. Most of you probably have seen it. So IceCube is an observatory, 1 kilometer cube volume, located at the South Pole, and they have 86 strings of digital optical modules, 5,160 of them, and it's buried deep, about 1 kilometer below the surface. Now, the way they detect the neutrinos is as follows. So if you have a very high energy neutrino coming in, then depending on what flavor of the neutrino it is, it will give you a different kind of signal. If it's a muon neutrino, then it will produce a muon by this charge current interaction, and the muon then will just leave a nice track in the detector. Okay, and this color coding here is basically showing the energy deposits. If it's red, it's higher energy, and if it's green, it's lower energy. So the muon here is traveling from this direction to this direction. And then if it's an electron neutrino, then it will produce electrons by the charge current interaction, and that will just deposit its energy locally, and it will give you a cascade, or what is called a shower event. Similarly, the hadronic leg here will also give you a shower event. So at the moment, ice cube does not have the sensitivity to separate the electromagnetic versus the hadronic showers, but they're working on it, and in the future upgrades, probably they will be able to distinguish the hadronic shower from the electromagnetic shower. And then if you have a tau neutrino, then something more spectacular could happen. So the tau neutrino produces a tau through the charge current interaction, and then this will the tau will travel some distance, and then it will decay because it's very short-lived, and then it can also produce another event. So this is called the double bang or the double cascade signature. Okay. And you can also have the neutral current interactions where you can also produce mostly the hadronic showers. Okay. So all these events, they are called, they're known as high energy starting events, or the HACI data samples. So IceCube has different types of data samples. They have the medium energy samples, and they also have what is called the through going samples and so on. But I'll be mostly focusing on this high energy starting event. So all this, so this basically means that the interaction starts within the detector volume, and then you see this kind of events. If the interaction is outside the detector volume, then they were not going to consider those events. Okay, good. So what do they see? So this is the latest from IceCube. This is, I think, 7.5 years of live data. And what is shown here is the deposited energy in the x-axis, on the x-axis, and then the events on the y-axis. So now this deposited energy can be translated into the actual incoming neutrino energy. So for electromagnetic and hadronic, it's a very well-defined process. And there is a known formula that you can use to translate this from the deposited to the actual energy. But if you have muons, then it's difficult because the muons don't deposit that much energy in the detector. So so they use what is called a proxy, and that has some uncertainty, even up to 20 to 30%. So you can only know the actual muon neutrino energy up to some extent, but you may not get the precise information. Anyway, so they have this all these data set, all these data points here, and what is shown in the color coding here. So this part is the atmospheric muon. This is a background, and this the other one, red one here, is also a background. It's from atmospheric neutrinos, and then you have in yellow is the astrophysical flux, which is the signal that they're looking for. Okay. So you can clearly see that the data is well above the background, and in fact, I think with 7.5 years, they have like in the 8 sigma or 9 sigma excess over the atmospheric background. So this is clearly extraterrestrial source of neutrinos, and the best fit solution seems to be a single component power law flux, unbroken power law flux, with the flux given by this just e power minus gamma. And the gamma is roughly 2.9. Okay, and this normalization is so given here. So of course, the error bars here are pretty large, and that's because they don't have much statistics yet. I think this is roughly 120 events, but with more and more data, they can constrain this further. Okay, so this is about the astrophysical flux. Now, with given this data, what can you do for new physics? Well, it turns out you can do a lot of things. And here is a picture which shows that. This is from a recent white paper. So you can affect, if you have new physics, then that can affect the neutrinos at different stages, starting from the source itself, all the way source and then propagation, and also at the detection. Okay, depending on what kind of new physics you have or what kind of new interactions you have, it can change either the energy spectrum that we saw in the earlier slide. It could change the arrival direction. It could change the flavor composition of the neutrinos, or it could affect the arrival times also. Okay? So obviously, I won't have time to go into all these different kinds of new physics scenarios. I'll just focus on a few of them. So mainly, I'll focus on these two: dark matter decay and the non-standard interactions. Then I'll also comment on the lepton and the supersymmetry scenarios. Okay, so what we do with the dark matter decay, and why do have dark matter decay in the first place? So isn't dark matter supposed to be stable? That's why it's dark matter, right? It has some relic density that we know. So why should the dark matter decay? Well, to be honest, we don't know anything about dark matter. So it can lie anywhere in this energy scale. And this is not a small scale, as you can see from here, many orders of magnitude. Okay, and dark matter could lie anywhere there. So for the ice cube, from the ice cube perspective, we can constrain if the dark matter mass is somewhere around this, and if it's decaying. I mean, of course, you can also look at the annihilation of the dark matter. That will cover a little bit below here in the weak mass range, but I'm just looking at the decaying dark matter scenario here, because this is something that no other experiment can do. Okay, only ice cube has such. They are seeing neutrinos with such high energy. They are some of the highest energy neutrinos ever observed. So we can constrain this very heavy dark matter using the ice cube data. So that's the unique feature of ice cube. Okay, so if you have PeV neutrino, PeV is 10⁻⁵ PeV. Okay, so this is really large energy. So if you have such heavy dark matter, what does it do? Well, it changes the spectrum. The spectrum that I showed you earlier, the single component unbroken power law flux. So that will be changed now. Okay, so you have an astrophysical component. On top of that, you'll have a component coming from the dark matter decay. Okay, so here is a picture which shows that. This is not the most recent one, because this paper was in 2018, but it gives the point. So you have this is astrophysical, the atmospheric background. Then you have the astrophysical part. Now, if you have just a single astrophysical component, that was the best fit at that time, e⁻².9, which is shown by this blue line. And now, if you have a dark matter contribution, then depending on the mass of the dark matter, you will populate anything below the dark matter mass, right? Because you hit a kinematic cutoff in the dark matter, you reach the dark matter mass, then you cannot produce any neutrinos above that energy scale. So that's why you have a kinematic cutoff. But below that, you can populate. Okay. And now we combine these two. So this is the combination. This is the dark matter plus the astrophysical combination. And it seems like just by looking at it by eye, you can tell that this fits the data better than just the single component power law flux. And moreover, if you have another component, then you don't need such steep powerless spectrum. Okay, you can just do it even e⁻². And e⁻² is something that is preferred from theory point of view, because most of the astrophysical sources which produce these neutrinos, they operate by what is called the Fermi-Salk acceleration mechanism, and it prefers e⁻² flux. Okay, so in fact, it's very difficult to get e⁻³ flux, as ice cube was initially suggesting. So if you have a second component, then it makes life much easier, and you can get this nice fit to the data. And now, if you translate that into the parameter space of dark matter, now namely the mass of the dark matter and the lifetime, then what you find is that this is the part of the parameter space which is preferred by the data here. Again, so the statistics is very low, so that's why you have only the 2 sigma, and the 3 sigma is kind of all over the place. But the point is that this gives a better fit than just the single component astrophysical flux. Okay. So now comes this multi-messenger connection, which makes it even more powerful. Okay. So let's look at the sources of the astrophysical neutrinos. So there are 2 kinds of sources typically considered. One is called the PP source, or the hydronuclear production mechanism. This happens, for example, in stardust galaxies or galaxy clusters, where you have a cosmic ray which is hitting one of the protons inside this astrophysical environment, and then from PP collision you produce pions, and then if you have neutral pions, they'll immediately decay to 2 photons. But if you have charged pions, they'll go to muons, and eventually they'll go to neutrinos, right? So this is a standard mechanism. And now, if you have, you can also produce by using P gamma collisions, and this happens, for instance, in photon-rich environments like gamma ray bursts, AGNs, blazars, supernova remnants, and so on, where you have P gamma interaction produces again, you produce pions, and then the pions will decay to muons and neutrinos, and then muons will decay to electrons and neutrinos. So in all of these cases, you can see this multi-messenger connection, that you start with a cosmic ray, and then you produce neutrinos. Along with that, you always produce some photons, because pions, and always you produce neutral and charged pions, and neutral ones will always give you photons. So there is a nice correlation between the flux of the cosmic rays, the flux of the neutrinos, and the flux of the photons. Okay, that's the multi-messenger connection. Okay. So now, if you take that and if you apply that to decaying dark matter scenario, then what you find is that, okay, so here is the case for the PP, and this case simply means that it's the ratio of the charge to neutral pions. So if you have a PP collisions, then you produce like both pi plus and pi minus. So the ratio is 2 here, and if you have P gamma, then the ratio will be 1, because you only produce the positively charged pions, okay? Because of the delta resistance. There's all this red part is excluded by looking at the gamma ray constraints. Okay, there is some old data for the very high energy gamma rays, and so we're looking at that. You can actually constrain this whole part of this parameter space. This is the photon flux and this energy, and so it seems like the single component astrophysical flux that ice cube has, so that's actually in tension with the gamma ray constraints. Whereas if you take either a 2-component astrophysical flux, or if you take one astrophysical plus a dark matter component, then that seems to be consistent with the gamma ray constraint. So that's the bottom line of this plot. And the same thing happens if you do the P gamma case. There also you find that the ice cube best fit is actually in tension with the gamma ray constraint. So again, so there's my preference for the dark matter. So again, I want to make a very big claim here, because because statistics is pretty shallow. So once you get more data, then we should be able to tell something more precise. But whatever data we have, it looks like the ice cube best fit for a single component power law is not consistent with the gamma ray.
Sorry.
Yes.
I'm trying to understand. So this scenario you're considering here, what you're saying, what you're calling decaying dark matter scenario, that's if it's in some mass range and there's some additional assumption that it does couple to neutrinos matter in some way, that it decays into, there's some decay that produces a neutrino, and why neutrino? Because if it produced something else, it would never reach us. So we're considering that scenario. Is that the logic?
Yeah, that's a good question. So yeah, so depending on what the dark matter decays to, the constraints will vary. So in this particular example, I have taken the dark matter decaying mostly to neutrinos, like a neutrinophilic dark matter, because that gives us the most stringent constraint. And now if you take, let's say dark matter decays to something else, let's say E plus E minus. But because the mass of the dark matter is so high, if it decays to E plus E minus, they are so highly boosted, then they'll just radiate off W bosons or Z bosons, and they'll eventually produce neutrino. So you'll always have some neutrino flux. Just that then the flux will be higher, lower, and it will be towards the low end of the energy spectrum. So the constraints will be weaker there. So what we're considering here is, even if you take the strongest constraints, then still the decaying dark matter is doing better than the just astrophysical flux. Now, if the dark matter decays something else, then these limits will become weaker for dark matter. So that will be even better scenario.
And what's the motivation for specifically, like, assuming it decays into something, just as like, if it only interacts rotationally, then that's the only way of detecting it. But what if it then we have this tool, or is there any sort of reason to expect this might be the case?
Right. I mean, yeah. So the reason why because we don't know anything about dark matter. So all we need is it has to be cosmologically stable, right? By cosmologically stable, I mean that its lifetime has to be longer than the age of the universe. In fact, several orders of magnitude larger than the age of the universe because of some CMB constraints and so on. So as long as it satisfies those constraints, then it can be decaying or it can be absolutely stable. Now, to make it absolutely stable, we need an extra assumption that there has to be some symmetry which protects it from decay, right? So that's an additional assumption. But in decaying case, you don't need that symmetry. So it just depends on what kind of model you're looking at. Some dark matter models, they just decay because there's no symmetry protecting them. And some cases there is some extra symmetry either put in by hand or by some residual symmetry where they are stable. So we're just probing the parameter space where parameter space of the models where they are decaying. Any other questions? Okay. So from the dark matter now, let me move on to something different. So as we just saw, the dark matter gives you a different spectral shape, and you can exploit that to put constraints on the dark matter space. So same thing you can do if you have some kind of new resonance at ice cube. Okay. So first, let's look at the resonances that happen in the standard model. So there's one nice resonance that happens in the standard model, which is known as the Glassware Resonance, proposed by Glassware in the 60s. I mean, that time there was no ice cube, but he was visionary, so he could see this. So if you have electron anti-neutrino hitting electron in the ice, then you can, if the energy is high enough, then you can produce a W boson on cell. Okay, and it's a very simple calculation one can do to show that the energy that needs to be the energy that you need has to be mw square over 2 times the mass of the electron. We know all these parameters, and if you plug in the numbers, you find it 6.3 PeV. So if you have a neutrino, electron anti-neutrino coming in with this energy, then you can produce a W boson, and then you'll see a nice hadronic cascade. And this was seen last year by IceCube. This was in this paper. They had just one event, but that was enough to establish that this process exists, and it has to if it is a standard model process. Now, what else can you do in the standard model? You can try to produce a Z resonance as well, because now if you have high energy neutrino, hitting a cosmic relic neutrino, we have this relic neutrino background all over. So if the energy is high enough, then you can in principle produce a Z boson as well, and that will also give you some cascade. And this was proposed by Tom Weiler in the 80s, and this is known as the G burst. But the bad news is that the energy that's required is much, much higher than the Glassware, simply because the neutrino mass is much smaller than the electron mass. Okay. And if you just again plug in the numbers, the highest, the upper limit on the neutrino mass from cosmology, then what you get is 10⁻14 GeV. And this is beyond what is called the ZZK cutoff. What this means is that to produce this neutrino in the first place, you must have some cosmic ray progenitor at that energy or higher. But the cosmic rays beyond the so-called ZZK cutoff, which is around 10⁻20 electron volts. So those cosmic rays, they'll always scatter against the CMB background, and they will produce deltas, and they will just go down to lower energy. So there is no way you can produce cosmic ray. You can have these neutrinos produced from the cosmic rays beyond the ZZK cutoff. So this process is unlikely to be seen unless there is some weird new physics that can enable these neutrinos to be produced, not through the cosmic rays, but through some other process. So in the standard model, it's just this Glassware, and that's it. So now, if you have some new particle, then you can produce resonance which looks like a Glassware. So here is an example. If you have some charged scalar, okay, now you can ask me, why do you need a charged scalar? Well, there are some models of neutrino mass, for instance, which need a charged scalar to give mass to the neutrinos at loop level. So you can take a charged scalar, and then it will look exactly like the Glassware resonance. Instead of a W boson, you just produce a charged scalar, right? So now there are limits on the charge scalar. You cannot make it arbitrarily light because there are limits from colliders, from other lab experiments. So the smallest you can make this is about 100 GeV, and you plug in that number, then it looks like, okay, so you can have like around 10 PeV resonance. And so we just call it Z burst, and not a Z burst, but a Z burst, because this is motivated by the Z model for neutrino mass. It's a very old model. In fact, one of the earliest models for loop level neutrino mass. Now, how does it look like in real life? Well, this is not real. This is simulated events. But if it has to happen, then it would look like this. So you would get some extra events due to this Z burst. Okay, and so right now everything is consistent with data. So all you can do is just put a limit on the mass of this particle and this coupling, because if you make this coupling larger, then you just make this rate go higher. Okay. Now, what is nice about this scenario is that the same interaction that we have here, that also gives you non-standard interactions of neutrinos. Okay, and that's it. We can just rotate this diagram, and that will basically tell you that you have neutrino electron going to, and if it's electron again, neutrino electron, then that will give you a non-standard neutrino interaction in the propagation of the neutrinos through matter. Okay. Similar things you can do also not with a charged scalar. You can do now with a colored scalar, which will be, for example, electroquark, or if you have some arc relative supersymmetry, you can have some quarks. and so on. And in fact, this was proposed as one of the possible explanations for some anomalous events that Anita had seen a few years ago. They had two upgoing events which were very hard to explain by any standard physics because they were traversing large distance in the Earth. They should be opaque to the Earth. Why should they travel thousands of kilometers? And one of the possible explanations that we came up with that it could be due to some long-lived particle comes from SUSY, and then that decays in the atmosphere and gives you some showers. And so far, I don't think anybody has ruled it out. So maybe something to watch out in the future. Okay. So how does the neutrino non-standard interaction work? If you have a neutrino in a matter interaction, and then if the energy of the neutrino is smaller compared to the mediator, then you can just write a Fermi interaction here. And this was done by Wolfenstein in his famous paper. The effect of this will be proportional to whatever coefficient you have, which is called the NSI coefficient. Now, in the case of the Z model, we have two such diagrams. Now you just open up this block, and you have this scalar mediation, and this will give you the non-standard interaction. So now this new scenario that IceCube has, the new resonance that we have, that actually gives a complementary probe of these non-standard interactions with matter in this mass versus coupling parameter space. So what IceCube right now constrains is this scenario, which is the dash line here, and then we just take future sensitivity of IceCube, just increase the exposure by, like, let's say 2 times the current exposure, or 4 times, or 10 times, or even 50 times. You're crazy. Then you get this kind of exclusion, future exclusion contours. Now, unfortunately, most of it is already ruled out by other experiments, the lab-based experiments, in particular IceCube itself, by looking at the low energy neutrinos, atmospheric neutrinos, and also Antares, which is its counterpart in the Mediterranean. And then there's a future experiment called Dune, which will probe this matter NSI to a large extent. And so those constraints will be somewhere over here. So the message to take from this plot is that although IceCube is not competitive enough to put any constraints at the moment, which are not excluded, but in the future, with higher and higher exposure, maybe they could probe some parameter space which is not probed by other experiments. But the question is, are we willing to wait like 300 years to do this? Probably not. But we can do something better than that. We can consider some other scenarios. For instance, if you have a pseudo-Dirac neutrino, what that means is that you can consider a maximally mixed superposition of active and sterile neutrino states, and with a small mass splitting between them. And you can now see what kind of mass splitting is probed by what kind of experiments. Okay. So if you look at all the lab-based experiments, they probe mass splitting like 10⁻⁵ electron volt square. So that's the solar, and then 10⁻³ which is atmospheric. But now if you go to higher and higher distance scales, then you can probe smaller and smaller mass splittings, right? And it turns out that from the sun itself, since we have seen the neutrinos from the sun, we can already constrain this mass splitting to about 10⁻11 electron volt square. But below that, everything is free, right? So whether it's really 0, which means it's exactly Dirac, or the mass splitting is non-zero, which means it's pseudo Dirac, that's not known. Okay. And so the high energy neutrinos, they are probing mass square splittings many orders of magnitude below what sun is doing. So like 10⁻17 or 18 electron volt square. So this is something that IceCube can do. And here is a plot just to show that. So now all these lab constraints are basically gone. Because what happens is that you produce these active neutrinos at the source, which is very far away, some megaparsec away. And then by the time it reaches us, it just has enough time to oscillate into a sterile state. So in the detector, it only participates as a sterile state, right? And in the lab, there is no way you can produce this sterile state with short baselines. So that's why all these lab constraints are not there, because you can't access it. The only way you can access it, this kind of state, is through this long distance effect. Okay, and that's what now IceCube can probe. And so the point is that we may not have to wait that long to get higher exposure, simply because there are other updates that are coming. And this is the plan for what is called a planetary neutrino telescope. So most of this is under construction now. So IceCube, of course, is running, and there's a version called IceCube Gen 2, which will expand this the detector volume by a factor of 10. And then there is also another experiment. It's called the Ocean Network Canada. It's off the coast of Vancouver, where they can also probe. I think they'll have also about 1 kilometer cube detector volume there. And there is also KM3 network in the Mediterranean, and also this in Russia. So together, they can give an exposure time which can multiply very quickly. You don't need to really wait for 100 years or 300 years to get the exposure that we need to prove those scenarios. So this is something interesting. Okay, so the next thing that I wanted to talk about is Relic Neutrino. Now, this is considered the holy grail of neutrino physics because this is something that we know it exists, but we have no way to detect it directly. Okay, and this is an open problem for the last 50 years. So what do the relic neutrinos do? So we know that the neutrinos decouple sometime before the Big Bang nucleosynthesis. So if you can detect the relic neutrino somehow, then you are probing the universe before the nucleosynthesis. Okay, and this is a unique probe of the very early stage of the universe. But this is very hard to do because these neutrinos are non-relativistic now, and so you can calculate what's the temperature of them. It's just related to the temperature of the CMB. With some factor because these are fermions, CMB photons are bosons, and so the temperature is 1.9 Kelvin, and that is roughly 10⁻⁴ electron volt. So these guys are non-relativistic, and you can also calculate the number density. Neutron star is about 56 per cubic centimeter for flavor. Now this number density is actually pretty large. If you compare to all the other sources of neutrinos, here is the plot showing the energy versus the flux. So the relic neutrinos are, they have the largest flux among all the sources of neutrinos. But simply because the energy is so low, so the kinetic energy in any interaction, they will have the kinetic energy that's imparted to the test particle will be so small that it will be very hard to detect. And that's the reason why it is so difficult to detect these relic neutrinos directly. But there are ways to do it, and so of course none of them has been successful so far. But one very nice idea is that if it can scatter against a very high energy neutrino and give you a resonant feature, like absorption feature. Okay. So the idea itself is pretty old. So the same paper that suggested the G-burst. So he also found out that if you have a high energy neutrino scattering against relic neutrino, then and if the energy is of this scale, then you can produce a deep feature in the high energy neutrino, and of course it will depend on the redshift. And so this is the survival probability of the high energy neutrino as a function of the energy normalized to the resonance energy. And if you go to higher and higher redshift, then you will see this effect more and more pronounced. Okay, so that was the idea. But the only problem is that we don't have such sources. Right? We don't have any source of neutrinos which can go to that energy. So the idea, although it's nice, it doesn't really work. So recently, what we found is that there is another thing that you can do. You don't have to rely on the Z boson in the standard model. You can do with vector mesons. Okay, and this is something that is similar to what happens in E plus E minus collisions, where you produce all these vector mesons. And this has been seen in the LEP experiment. They have now, this is textbook material. They saw this plot of the E plus E minus rate to hadrons versus E plus minus to muons. They saw these nice step functions and so on. So you can do exactly the same thing with neutrinos now, because they're part of the SU2 doublet. So they also interact with the mesons the same vector interactions. They also have axial vector interactions. So you can produce all those vector mesons and axial vector mesons. Okay. Now the only advantage here you get compared to this is that the mass of the meson is much smaller compared to the mass of the Z. So now the energy that you need is it's like 4 orders of magnitude smaller. So this is accessible at the neutrino telescopes. Okay. So this is a new way to look for the relic neutrinos. Okay. So how does it work? Well, there is actually another nice numerical coincidence that happens. So if you look at the very high energy neutrino flux, what is called the Decaying neutrino flux, you find that the peak of that flux is happening exactly at the same energy where you would expect the rho resonance peak. And this doesn't have to be. This is completely a numerical coincidence, because this peak is coming because of the delta resonance, delta baryon, which decays to then pions, and that gives you this neutrino flux. And this peak has, and then for the rho resonance, has nothing to do with the delta. It just happens that the masses are in such a way in the standard model that this exactly happens at the low resonance speed. And that gives us nice handle on using this effect to probe the relic neutrinos. Okay. So what is shown in this plot are I think the current sensitivities of different experiments like Anita, Oje, and so on, and then the future sensitivities of various different experiments. Most of them are radio based, like this ice cube Gen 2 radio and Brian and so on. I think Brian is part of this PUEO experiment, which is led by the UC Carbon group. So you can see that all these experiments have sensitivity to this part of the parameter space where they can really find this GZK neutrino flux. Okay, of course, assuming that this is the cosmic ray, this is the primary cosmic rays from the proton and not from the heavy nuclei and so on. There is some uncertainty there, but apart from that, you might be able to see. So now let's superimpose our rho peak on that and see what happens. So of course, that will depend on the energy, that will depend on the mass of the neutrinos. And if you take the mass of the neutrino, the lightest neutrino to 0.01 eV, then you would get this two kind of dip feature. Now you can ask me later why two dips, why not one? But let's keep on increasing the neutrino mass, and then you see that these two peaks, the two dips now merge into one. If you increase the mass, and if you increase the mass too much, then you get a spectacular nice feature. So of course, this mass is already ruled out from cosmology, but these masses are still allowed, and then you could see this kind of deep feature in the high energy neutrino flux. But the only issue is that you need some large overdensity for the relic neutrinos to see any observable effect. So here we have taken like 10⁻11. So here is a plot which shows this the overdensity as a function of the lightest neutrino mass. So to get this effect, you need to have this overdensity of 10⁻11 or something. But this may not be that crazy. Well, partly because another experiment is constraining the same parameter space, and this is the Catherine experiment, which is running in Karlsruhe, Germany. So they are looking basically for the lightest mass of absolute mass of the neutrino by looking at the beta decay endpoint, and they can also do the beta capture of the tritium, helium, and electron, and then they look for the energy spectrum of the electron, and they can also constrain the overdensity. And recently they had a paper where they put a constraint which is around 10⁻11. And what we find is that with this high energy neutrino experiments, you can actually probe similar overdensity in this in this part of the parameter space. Okay. So the only I mean, if you want to just do the comparison, the Catherine limit is only sensitive to the local overdensity, like around the Earth, because the experiment is located on the Earth. Whereas the mechanism that we are proposing here, that is sensitive to arbitrary redshifts, because the source can be anywhere in the sky. Okay. So of course, if you go to higher redshifts, then the effect will become more and more. But you cannot go to arbitrarily large redshifts, because at some point the star formation rate will die around G equal to 4 or 5, and after that you don't have any sources at all. So you cannot go arbitrarily high, but of G equal to 2 to 3 is I think fine. Now the other thing that we require here is that we need to have some anisotropy in the source distributions, which will enhance the effect, because if you make more and more such overdense regions, then the size of each region will become smaller, because the total number has to be conserved. So if you have just one cloud, then you get the highest effect. If you have more clouds, then the effect will become smaller. So now, can this be seen? Well, there is some hint actually for this anisotropy, but it's inconclusive, because it could just be due to some magnetic field effect in galactic magnetic field. So very hard to actually probe this cosmic ray anisotropy. I mean, there are experts in this room, maybe they can comment on this better. But in the future, with more data and with better cosmic ray experiments, maybe we'll be able to do this. Okay, so the last thing about this neutrino clustering. You could ask, like, how do you get such large overdensity? Well, one way is to do the gravitational clustering. Because neutrinos have mass, they can just cluster gravitationally, and then maybe they could explain overdensity. Well, there's this simulation done by this Daisy group, which found that it's actually not possible to get such large overdensity. You can maximum get maybe up to 1,000 or something. You cannot get higher. But they only did it for the galactic. They just take the scale of the galaxy, and then increase the, take different masses of the galaxy and then different masses of the neutrinos, and this is what they have done. So this is not enough. Well, is there any other way? Could be if we take some help from some new physics. And one possibility is to have a neutrino self interaction. Okay? So it's like just a Ikawa type interaction now with a new scalar. And if the potential energy, if the kinetic energy less than the potential energy, then it can form a bound state. And this happens for this particular combination. And these people, they did a simulation, semi-analytic simulation actually, and what they find is that you can get over density up to 10⁹. So this is coming very close to what we need to get the effect that to be comparable to scattering. But there are other issues here, like you can form a medium dependent correction to neutrino mass, and that puts a constraint on this. So it's not very clear how large can we push it further. But in general, the clustering in dense environments is still an open problem, in my opinion, because these people have only done it for galaxy. But if you have some more, dense impact object, then maybe you can have a larger clustering. And this is something that hopefully somebody will look at in the future. Okay, so I don't have much time left for my part 2, but I'll just briefly mention a couple of things about part 2. That we can also do new physics with gravitational waves, since I mentioned gravitational waves. And one thing that you can do is a first order phase transition. Now, what is a first order, what is second order? This you can you probably have seen in your thermodynamics course. And that if you have a wave of a scalar, then if the wave is continuous, it is continuous, then you get a first order. Whereas if the wave is continuous, you get a first order, second order. So the second order is boring because it does not give any interesting features that we are looking for. And the first one is interesting because it gives us something nice. And that nice thing is shown here. If you have a potential, then if you have the first order transition, then you can do the tunneling from the false vacuum to the true vacuum. And so if you do this, then this goes via this bubble nucleations, and here you can produce gravitational waves. And this is what this is something that, for example, gravitational wave experiments can see. Okay? And this is not something that we just make up. There are many well-motivated BSM scenarios which actually give you this kind of potential. So one example is axion. Okay? And there are many people in this room who love axions, and for good reasons, because they solve the strong CP problem. Now I don't have time to go into all the details, but so what happens is that if you write a complex scalar field, then the angular part that gives you that's basically the axion, that's the pseudo Navier-Goldstone boson. But there is also a radial part here. Okay, and the radial part gets a mass which is close to this symmetry breaking, the U1 symmetry breaking scale, which is around which is FA, right? So which is a free parameter model. So now you can induce a first order phase transition if this guy couples to Higgs. So if it's standard model Higgs, then there has to be some fine tuning. But if it's some second Higgs, then you can do it very easily. Again, I don't have much time to go into all the details, but here is a plot which shows this. There's some work done with Francesc and his student Yang and my postdoc Yang Chao. So if you look at the potential and then as a function of this the field for some values, then you can see that you can clearly get a first order phase transition, okay, in this scenario. And what it does, it produces gravitational waves, and this could be detectable in the future gravitational wave experiments, right? So there are many experiments listed here. Maybe you can't see it; it's too small. But here is a better picture where you can probably see it more clearly. So there are many experiments that are proposed, both ground-based and space-based, where you can probe this the axion decay constant. And this is a complementary to the lab probes that we are doing, for example, the ADMX. So they are probing this same parameter space, mass versus coupling to photons, for instance. And so what the gravitational waves do, they are independent of the mass of the axion, because this is the light mode, and they are only sensitive to the heavy mode. So they probe this independent of the mass, but this coupling is related to the 1/FA. So depending on what range of FA you can probe, then you can probe a given range of the coupling here. Okay, so that's one. So there's a nice complementarity between the gravitational wave experiment and the other lab probe of axions here. Now this probably maybe I'll just mention one quick thing here. So there's another very interesting thing in axion physics, that there is so-called this cosmological triangle. Now there is this parameter space here which is not constrained by anything, any lab-based experiment at the moment, except for cosmology. But the cosmology bound is model dependent, because it depends on the cosmological history of the axion production and so on. So it would be nice if we can have some other independent probe of this scenario. And one thing that one could do in principle is what is called this Primakov process, where the axion, when you can produce the axion from the photon interactions with the nucleus or with the electron, you say, and then axion can decay to photons, And these photons, because this falls exactly in the MeV range, so we can detect it using the future MeV missions. Like for example, the mission of Jim, which he claims that has the highest sensitivity among all the other experiments, right? Which would be good. And this is complementary again to another lab experiment, which is the Dune, which can probe also axions using either inverse Primakov, where the axion goes back to photon, or the axion can decay also in the detector, and you can probe this. So this gives a nice, again, complementarity between the astrophysical observations versus the lab-based observations to probe this hole in the axion parameter space. Okay, so I think maybe okay, so I'll probably skip this, and then I'll just conclude that yeah, of course, we need combined efforts at multiple frontiers, energy, intensity, and cosmic, in order to probe new physics. We don't know exactly where it will manifest, but the detection of these high-energy neutrinos and gravitational waves, they have opened new windows of opportunities for us, and they give complementary probes, to the lab searches. So the future looks promising because of all this new array of experiments, and it looks brighter than ever. So with that, I'll stop. Thank you.
Are there any questions?
Just explain again how this cosmic overdensity is defined.
Oh, you mean the Relic overdensity? Yeah. So we have this. Maybe I can explain it here. So we have this the number density that's just proportional to the temperature Q, right? And just because we know the temperature, which is related to the CMB temperature. So from there, we get this 56 per cubic centimeter. So that's the standard scenario, right? So now if you have either some self-interactions of neutrinos or some clustering other than the gravitational clustering, then you could get overdensity, which will, so let me call it mu zero. So which will be some factor times this mu zero and 1 plus g cube. Because you're looking at the higher redshifts, you're looking at smaller parts of the you're looking at the universe was smaller there, so you have this 1 plus g cube enhancement, but also you can have this overdensity factor. So we don't know what this value is, so this is what we are trying to constrain using this high energy neutrinos. Right. I don't know if that answered your question.
I have a question about the dark matter decay.
Yes.
So this is the decay of the dark matter where?
Decay of the dark matter in the galactic halo or in the dark. Yeah, wherever we have dark matter.
So that's the thing, it's not the dark matter from the source, from the AGN, right? But these neutrinos are...
No, it has nothing to do with the source. Because the source
this should be an isotropic or mostly isotropic component, right?
Yeah, and the source is also isotropic. I mean, more or less isotropic. We don't have any directional sensitivity for the physical source.
Okay, so these neutrinos are not the neutrinos that have been seen not the PeV neutrinos.
Sorry, which ones?
So, I'm trying to understand. The neutrinos, the PeV neutrinos that you showed in the beginning, those we know that they come from a blazar, or some of them.
Right.
So,
yeah, but not all of them.
Not all of them.
Right.
You are not referring to these neutrinos. You're referring to the ones that don't come from the blazar.
Yeah.
This is the isotropic component.
Exactly. That isotropic component, I mean, Ice Cube has given the sky map and it looks pretty much isotropic. Yeah. So it could be coming either from astrophysical sources, like maybe some other blazars or GRBs or whatever, or it could be coming from some dark matter decay. Now, I think the galactic component here would be small. It's the extragalactic component which will contribute more. For the so for the astrophysical, we know that the galactic component is very small, but for the dark matter, it could be there, and in fact, they can contribute almost equally.
Yeah. There would be an asymmetry because we are not in the center of the
Exactly. Yeah. But that effect is not observable with this data. In the future, yeah, you're right. We can distinguish this, and then we can probably tell whether it's really from dark matter decay or not.
So, but then what does the matter? Dark matter must have to be PeV, and those neutrinos are GeV. So,
which are GeV? Sorry. Oh, you mean here?
Okay, so yeah, I'm trying to understand the scale.
Yeah, this is from the cascades, right? Because the dark matter can decay to neutrinos, let's say we have a fermenting dark matter, I that goes to electron, and it goes to, let's say, W, and W goes to L and U. So this is one source of neutrinos, right? So now, so of course this neutrino energy will be smaller than the mass of the dark matter, but then these electrons, because they're so highly energetic, they can also radiate off as D, and then Z can go to mu bar. So they will also get secondary neutrino. So that's what you have to see this tail here. That's populating, these secondary ones are populating the low energy.
But I would also expect up to PeV neutrinos from this.
Well, so here I've taken the energy, the mass of the dark matter to be 100 TeV. So that's why you see a cutoff at 100 TeV.
Okay.
Yeah, I mean, it's just a choice that I've chosen, I made here. But then the other plot shows the actual, the whole range, right? So yeah, so this is about like 300 TeV, I think. That's the best fit that we get from this. I mean, we do it for different masses, of course, and get the best fit. And then this is the 2 sigma sensitivity range. Yeah. So it's only sensitive to some part of the parameter space. I mean, that was partly because, there are some mild excess here, as you can see. And so, so if you have dark matter around this mass, then it would be able to explain this better. And that's why it is kind of hovering around this range. Yeah.
Yeah, just a follow-up to Francesca's question. I don't understand why the galactic center wouldn't dominate, because even for, unless it's some sort of a Olbers paradox thing that you can see out further, but for decaying dark matter, you would still, I know for annihilating dark matter, the galactic center would definitely dominate, but that goes like density squared, but you still see, I think when you still see the galactic center, it's the.
So,
the galactic center region.
yeah, we did look into it. I mean, this was a while ago, so let me try to remember. So you would get some excess from the galactic center. I think for annihilating it, the effect is more pronounced than the decaying.
Right, it's
Because it's
definitely more
density.
pronounced, and then there's
Exactly.
another slightly weird thing, which is that the universe is transparent. Well, yeah.
Right, and it also matters like dark matter decays to what? If it decays to mostly charged particles, then they'll lose energy very fast in the galactic center.
Right.
And then you won't get many neutrinos from there. So
You get synchrotron.
exactly. But if you're in the other part of the sky, then you can more efficiently get the neutrino out. I mean, the neutrinos always come out efficiently, but it's the charged particles which produce the neutrinos, and those are either if they lose energy much faster, then you won't get the neutrino flux that efficiently. So that is one of the reasons why we're not so much sensitive to the galactic center for the decaying case. But of course, I mean, there will be some sensitivity once you have a lot more data, then you will be able to distinguish preferentially.
Last question.
Just a very quick question. What is that 30 solar mass?
Good question. Yeah. So this is basically all the possible mass scale that we can have for dark matter, and it can be particle-like dark matter, which can have energy mass all the way up to Planck scale, and then you can also have composite objects as dark matter, like primordial black holes, for instance, and they can have mass of 10 solar mass or 30 solar mass. In fact, after the LIGO discovery, there are a bunch of papers which try to say that you can have primordial black holes as the dark matter candidate. But now, of course, I think they're mostly ruled out by microlensing and other data, but they can still be a fraction of the dark matter. They may not be the 100% dark matter, but there is tiny. I forgot like how much fraction, maybe -4 or -5, something like that. They can still be. So yeah, dark matter could still be such heavy, and it could still contribute part of the relic density. Yeah.
Let's thank Bhupal again.